All right, so in this case, we are looking at a beam here that has a mass of M and a length of L. It's being held in place by some sort of cable, and there is a hinge here. So what I'm looking for here is I am looking for the value of the magnitude and direction of the force of the hinge on the beam when in equilibrium. And this is actually a pretty tricky question. So basically, if you think about like the way a hinge works, a hinge kind of resists motion. There's usually some sort of socket that the hinge sits in, and that basically as you try and turn, the hinge is keeping it in place so that it doesn't like fall and stuff, that it stays in the same location. Now, the direction of this force can change. Sometimes the direction of that resistive force, which we usually just call FR, R for resistive, is actually just perpendicular to the, the wall type idea. It can be there. But basically, if I'm going to hold this in place, this resistive force is going to change. If I pull down on this more, then what's going to happen is that force might have to be upwards at an angle. Or maybe that I'm not pulling up enough and it has to help counteract. Or maybe it's getting pulled down more, and so it can be at like different angles. So this force is completely variable. Now, technically, this resistive force is the sum of normal force and friction. I don't know if I wrote that at an angle. It's the sum of the normal force and the friction force, because the friction force would have a component that would be parallel to the wall, and the normal force would have a force that's perpendicular to wall. So the resistive force would be the vector sum of those. So if there's only a normal force, then the friction force would be 0. But collectively, if I'm looking for the force of the hinge on the beam, I'm talking about essentially the net resistive force, which is the vector sum of these. Okay, but generally it has two components, one of which is going to be a normal force and one of which is going to be a friction force. Or depending on the type of hinge, it could be two different normal forces, or it could be a normal force at an angle. So if I had like a socket here, it's possible to have that socket exerting a normal force at various different angles, depending on where the force is being applied. But regardless of what these forces are, when you are working a problem like this, you need to always assume that resistive force has X and Y components. So you need to include them in your diagram. And you can include them wherever. Like, I don't know where those components are. Now, I probably know that the X component is pointing out. If there is an X component, that the FRX is probably pointing out. But whether there is an FRY or whether that FRY is up or down, I don't know. So I can just assume that FRY is up and just define my FR for my thinking process in any direction I choose. Now, the reason this works is if you assume incorrectly, there's some different options. So if one of the components comes out negative, then all that means is that the force was drawn in opposite direction. Now we're going to do this one non-numerically, so I'm not going to have numbers, but it'll give you an idea of what I mean. So, for example, if I assume that FRY is up, and in reality FRY is down, then when I go through and do my math, FRY would calculate out as negative when I put it in this location, positive if I put it down here. So it coming out as negative just tells me it's not up, it's down, okay? And if there is no FRY, if a component calculates out as 0, then there was no component. And that just kind of makes sense. So our assumption that FRY is up and has a value could actually be incorrect if it calculates out as 0. So if it calculates out as 0, then that's like, oh, well, I didn't need that anyways. So, but if you don't include the components in your diagrams, in your setup, and they exist, you will get the wrong answer. So if you don't include components, if you don't include a component, and that component exists, then you will get the wrong answer. I cannot stress that enough. So you have to assume that it always has 2 components, because if you don't, you will get a wrong answer. If you assume and it's not there, it'll just come out as 0 and it'll say, hey, you didn't actually need it. It calculates as a 0. But if you forget about it and it's there, you will get the wrong answer for all of your other values. Or maybe not all of your values, but a lot of your values. So that is kind of the first thing. So you can also guess the direction, well, logically reason what the direction is just by looking at the forces. Because one interesting thing about rotational equilibrium is that to be in rotational equilibrium, you have to be in equilibrium about all axes of, rotational equilibrium. Your net torque must equal 0 about any axis of rotation. Well, no. To be in static equilibrium, which is what this is, because it's assuming it's not moving, then basically your net torque has to equal 0 about any axis of rotation. Any and all possible axes of rotation. Because even though I might assume that the axis of rotation is actually the hinge, technically I have to be, every point has to be in equilibrium. So what I can do is I can test where the forces are acting at different locations to figure out where this resistive force might be. So let's take a look at how that might happen. So first of all, let's start by drawing our extended body diagram by including all of our forces. So I'm going to start with the forces that I know for sure the direction. So for example, if there's a cable here, there's going to be some sort of tension. So I'm going to label that as a tension force. Okay, there's going to be, this board has a mass, so there's going to be a force of gravity. Where does that force of gravity get drawn? If we assume this is a uniform board, then it gets drawn at the center. If it's non-uniform, then they are going to tell you specifically where that center of mass is, and that's where you would draw it. Okay, so that's going to be at a distance of L over 2. My tension force is going to be at a full distance of L, so those are those lever arms. And with my resistive force, let's see, how do I figure out what this is? Well, let's consider some axis of rotation. The actual axis of rotation that we're going to analyze, this thing is actually rotating about the hinge. That's kind of how this system is going to work. But my resistive force, wherever it points, is located at the axis of rotation. So the resistive force exerts no torque when choosing the hinge, about the hinge as the axis of rotation. So if I want to learn more about where the force is pointing, then I need to consider a different axis of rotation. So there's a couple of different locations that would be good. One would be the center of mass, because if there was no hinge, objects tend to rotate about their center of mass. So if I were to choose the center of mass of that board to be the axis of rotation, then the gravitational force would exert no torque. This tension force would exert a torque. It's going to exert a torque about this axis of rotation in this direction. So that means that in order for this to be in equilibrium, there has to be something causing a torque in the opposite direction, which means this resistive force has to be capable of supplying that torque, because there are no other forces. So where would that resistive force need to have a component? Well, it for sure would have to have a component basically up, because if it had a component just horizontal, sideways, then that would be parallel to the lever arm, which would be this location right here. So therefore, so the lever arm would be here. So that would be parallel. So a parallel component cannot cause torque. So, and I need the torque to be in the opposite direction. So if my resistive force has a torque, force upwards, that torque would cause a rotation in that direction. So I know that at least some component of that force has to be upwards. My resistive force does have to have a y component. Now, does it have to have a horizontal component? Well, that I can actually look at my force balance. So because this tension force has an x component and a y component, I know that this resistive force is going to have an x component, because the gravitational force here is pointing straight down. There's no other forces to counteract that horizontal force, because I need to be in both rotational equilibrium and static and translational equilibrium to be in static equilibrium. So that means that I must also have an x component. So it's likely that this resistive force is going to be pointing somewhere up and to the right. Now, I don't know what angle it's at, so I'm going to need to kind of look at those components individually in order to solve this issue. So I know that for sure. And if I were to choose a different axis of rotation, I can still prove that that has to be there, because if I were to say choose my axis of rotation to be the end point here, then my tension would not be exerting a torque anymore, because it would be at the axis of rotation, but this gravitational force would be, and it's going to be acting down, so this one would be causing a rotation in the counterclockwise direction, which means in order for this to be in rotational equilibrium about this point, then once again there would have to be an upward component in order to cause a torque that is in the opposite direction to this torque due by gravity. So that's two different proofs that there has to be a y component to that force. So now that we know where the forces point and where the components kind of are, we can write our net force equations and our net torque equations, because that is going to be our next step. So I'm going to start with a clean board here, so we can kind of go through and label it, because we had a bunch of different axes of rotation there, which was kind of confusing. So once again, the forces that we have acting are tension, acting along the rope. We have a gravitational force acting at the center of mass, and we have identified the resistive force as being up and to the right. So those are my different forces. Okay, this is an extended body diagram because I've drawn them where they act. So this tension's acting here, gravity's acting at the center, and so forth. I need to also identify their lever arms relative to the axis of rotation. So if I set my axis of rotation to be the hinge, okay, then I can identify my lever arms. So the lever arm for the resistive force is 0 because it's at that axis of rotation. So when we write our net torque equation, we're not actually going to need to include the resistive force, which is nice. So I am going to have a lever arm for tension. So the R for tension is going to actually just be L. And the R for gravity is going to be L over 2 because it's acting at the center of mass. So it's half the length of the board. Now I could have chosen any axis of rotation, but because it doesn't tell me I'm looking specifically about the hinge, but that's where we know it's rotating about, so it makes sense. But in some situations, like, you won't know the exact axis of rotation, or the exact axis of rotation doesn't matter. For example, one of the ones on your homework assignment, has two different pillars. And it's like a bridge type situation. There's like a car on the bridge somewhere, and etc. And we want this to be in equilibrium, and we're looking at maybe what one of the forces is or something. So where would the axis of rotation be on in this problem? Well, it could be in different locations. The axis of rotation could be the center of the bridge. The axis of rotation could be one of the pillars, or it could be the other pillar. The axis of rotation could be the end. You can actually make your axis of rotation anywhere you want. But when you're choosing your axis of rotation, generally you want to choose your axis of rotation to be somewhere where you have unknown forces. Why would I want to put my axis of rotation where I have unknown forces? Well, if I place my axis of rotation where I have unknown forces, then what's really cool is those forces don't exert torque. So it eliminates some unknowns from my calculations. Now that unknown force will still appear in my net force equations, but it won't appear in my net torque. So that will actually simplify things down again. So if you aren't sure where to put the axis of rotation, one of the easiest places to put it is where there are a lot of unknown forces. Now, what if you don't choose the location with most unknown forces? What if Mrs. Humes in her answer does this one and you choose that one instead? That's okay. You will still be able to arrive at the answer in most cases. You just might have to do more work and more steps in order to get there. There are easier ways and harder ways, and a lot of that's dependent on where you choose your axis of rotation. And that's going to come with experience. So just realize if you choose the wrong axis of rotation, you can still solve it. You just might have to do more algebra steps along the way. All right, so now that I've identified my axis of rotation, my lever arms and so forth, I'm actually going to take a look and resolve these forces at angles into their components. Now remember, if it was asking you for an actual free body diagram, you should never do that. But in this case, because this is a working diagram, I'm going to show those components. So I'm going to have an FTX and I'm going to have an FTY. Now I know that these are related to this angle theta here, but this is not necessarily at that same angle theta, so I don't know anything about that angle, so I'm not drawing a symbol for that angle. So I'm going to have FRX, and I'm going to have FRY. So then what I do once I've labeled all of my components and so forth, then I write the conditions for equilibrium. So in this case, I know that my net force has to equal 0 because it's not translating. And I know that my net torque has to equal 0. But this is a problem in 2 dimensions. So that not only means that my net force is equal to 0, my net force in the x direction has to equal 0, and my net force in the y direction has to equal 0. So I actually have 3 different equations that I can work with, which is good because I've got multiple unknowns. Actually, in this case, I have 2 unknowns, FRX and FRY. Well, and also the angle. So I could actually have 3 unknowns. So with this information, I could actually find FRX, FRY, and the angle that they're acting. Now, we're looking for the magnitude direction of the force of the hinge on the beam. So we are looking for FR, and I'm going to call this angle phi right here. So I'm going to call it phi, not theta because that one's theta. So we're going to look for phi. We need to find those 2 pieces of information. So once I've identified my conditions for equilibrium, these provide equations for which I can work. So I usually start with the net force equations because I am more comfortable working with forces than torques. So I'm going to write my net force equation in the x direction. My net force equation in the x direction is going to be my positive forces, which is going to be this FRX. So that's this positive resistive force going to the right. And then this tension force is in the opposite direction, and those have to add up to 0. In the y direction, when I look at the y direction, I'm going to have FRY going upwards. I'm going to have FTY going upwards. And I'm going to have FG coming down, and that has to add up to 0. For my net torque equation, I'm going to have my clockwise and counterclockwise torques. So about this axis of rotation, this force exerts no torque. And if I look, gravity is going to cause a rotation that way, which is the negative direction. Tension is going to cause a rotation this way, which is positive. So once again, I can figure that out by pointing my fingers in the direction of the lever arm, rotating my palm to the force, curling my fingers, that shows the direction of rotation. The torque force is actually out of the page for that tension. So that means I can write the torque due to tension minus the torque due to gravity, and that has to add up to 0. So this is one of the most important steps, because if these equations are wrong, then you are unlikely to arrive at the correct answer. Okay, and once again, you would always assume that your resistive force here at a hinge has an X and Y component unless otherwise told. So breaking these down, I know that FRX is going to equal FTX. And I know that FTX, if I look at this, is going to be, oh, I don't know my tension force, so I actually have another unknown there. So I don't know my tension. So my tension is a huge unknown. So that's going to be tension. The X component is the adjacent side, so it's going to be FT cosine theta. When I look over here in the Y, I'm going to have FRY is equal to FG minus FTY. So FRY is going to be mg minus ft, and then fty is the sine theta. And then if I come over here to this one, I'm going to have the torque due to ft is equal to the torque due to fg. So my torque due to ft is going to be based on the perpendicular component to r, which is going to be fty times RT. The torque due to FG is going to be FG. It's already perpendicular, so it doesn't have an angle, times RG. And then FTY is going to be, once again, FT sine theta. RT is L. FG is going to be mg. RG is L over 2. So you can see they don't actually have to give us the length of the board, because the length of the board actually cancels out. So if I look at these equations that I have here, I can look at my unknowns. And I don't know FRX, I don't know FRY, I don't know FT. So that's 3 unknowns. FT I'm not interested in. So what I want to do is I want to eliminate FT from these equations. So I can do that. For example, if I look over here, I can solve this one for FT because it doesn't involve FR. It's useful to use this one, and that's going to be mg over 2 sine theta. So I've actually found the tension. It didn't ask me for it, but I could find it. So my tension force can then get plugged in into both of these equations. So I find that FRX is going to be FT, which is mg over 2 sine theta times cosine theta. All right, so I have FRX. I can come over here and find FRY. FRY is going to be mg minus FT is mg over 2 sine theta times this sine theta. And I can see that the sine thetas cancel out. So I get mg minus 1/2 of mg, so I get FRY is equal to 1/2 of mg. So I do actually need a y component to that resistive force. It's equal to 1/2 of the gravitational force of the beam. And then FRX is equal to FTX. So that's really a kind of cool factor there as well. So one thing that I notice is that FTY is actually going to equal FRY, because FTY is, if I actually go back up here and I look at this, if I do FTY is mg over 2 sine theta. So FT is also going to equal 1/2 of mg. Because this is FTY right here. So FTY is equal to 1/2 of mg. So FRY is equal to 1/2 of mg. FRX is equal to mg over 2 tan theta, because FT was ftx is equal to mg over 2 sine theta. So, or ftx is equal to ft over here. So frx and ftx are actually the same. FRY and FTY are actually the same. So what that tells us is because FRY has the same magnitude as FTY and FRX has the same magnitude of FTX, that actually phi and theta in this case are actually the same value. And you could actually go through and find what those values are. So if I wanted to find FR, which is actually what the question's asking, FR is going to be the square root of FRY squared, or actually I usually do X first, plus FRY squared. So FR is going to be the square root of FRX squared, which is going to be mg over 2 tan theta squared, plus FRY is going to be 1/2 mg squared. I'm not going to simplify that down, but if I wanted to actually find the magnitude of FR, this is the magnitude of FR. If I wanted to find the angle phi that FR is at, that's the direction. So my angle phi is going to equal the inverse tangent, or tan, of FRY over FRX, because that's the definition here based on tan theta being FRY over FRX. And if I sub in, FRY is 1/2 of mg, FRX is mg over 2 tan theta. So if I go through and take a look, I get mg's cancel on top and bottom. This is a 2 on the bottom, that's a 2 on the bottom, so those cancel. And that's going to bring the tan theta up to the top, so that's going to give phi is tan to the -1 of tan theta. So that tells us that phi is equal to theta. So the direction though is going to be relative to the situation would be above the horizontal. Towards the right. Oh, it's not a really good way to put it, but if I had to describe the direction of FR, it's above the horizontal and towards the right at this angle of theta. Or I could maybe do above the right horizontal, I don't know, something along those lines. So sometimes you won't have to go through and find the whole magnitude. For example, if you just wanted the X and Y components, it would be something along these lines, and then that would give us the direction. So you have to be careful because these problems sometimes change up. This is not true of every situation. That was only true because we just had the beam and the angles and so forth there. You'll see these, like I've seen them where there's like a lamp here at the bottom, or sometimes there's someone standing on the beam for some reason. And sometimes the sign is in different locations. Sometimes the beam itself has no mass. There are a lot of variations, and every variation is going to result in something different. You're not going to get the same result. So that was just a special cool thing that the angles were the same here. That is not a general solution to all problems like this.